Hello chemists, I'm about to talk to you about mass spectrometry. Mass spectrometry is the first of the three types of spectrometry that we'll be covering as part of this topic. Mass spectrometry is the science of using magnetic fields and measuring devices to measure the mass of different fragments of a complex organic molecule. For the way that it works is you take a organic molecule, such as this one right here, for example, you put it into a machine and the machine does some terrible science to it. The first thing that happens is the molecule gets bashed into little tiny bits right here by an electron beam. Each one of those little bits will then be sped up quite fast by an electric field or the accelerator plate here, and then it gets shot out in a beam of ions there. Each one of those ions, each one of those fragments of the original molecule has got a charge. It's got a charge because it has been bashed apart. When you break a molecule right here, those ends no longer have anything attached to them. You then have a molecule that is missing a proton, missing an electron, and it is then going to have a positive charge. So that is an ion. Those ions move into a magnetic field here provided by the magnet, and based on their mass and their charge, and in fact the ratio of their mass to their charge, they're going to bend. Their flight path is going to bend until they change their path and they run into a plate down here that detects them. And based on the ratio of their mass to their charge, if something's got a high mass but a low charge, it won't bend very much. If something has a low mass and a high charge, it will bend quite a bit. Based on that bend, they will move and be detected by this detector right here. And that detector will output a graph that looks like this. And this looks terrifying, but is in fact not too bad. What each one of these peaks, what each one of these lines indicates is a mass to charge ratio, which is a complicated way of saying how much a chunk of that molecule weighs. There will be one peak at the very top, the peak with the highest number, which is called the molecular ion. Basically, that's the whole molecule, but the piece that has been bashed off is a single electron. So it's the whole molecule minus electron, which has the same mass as the whole molecule. You will also have one really, really tall peak. That's called the base peak, and that is the most common fragment. You'll also have several other peaks, each of those corresponding to a different possible fragment of the molecule. And what do I mean when I say possible fragments? Well, when we take our molecule right here and bash it into a million bits, each one of those bits comes from a broken bond. So for instance, the bond could break here, or here, or here, or here. So any place there is a bond, there is a possible break. And some of those breaks are more likely than others. For instance, a single bond, such as this one here, is more likely to break than a double bond, such as that one there. So your fragment that is this portion of the molecule is much more likely to happen than your fragment that is this portion of the molecule, because this one results from the breaking of a single bond and the other one results from the breaking of a double bond. So this fragment of a molecule right here consists of a carbon, an oxygen, a hydroxide, and that is it. So it's going to have a mass of a carbon, an oxygen, and a hydroxide all put together. So carbon is 12, oxygen is 16, so 32 plus 12 is 44, plus 1 is 45, so we'd expect to see a peak at around 45, which I believe is going to be that peak right there. We would also expect to see a peak at the mass of the whole thing, which is carbon plus carbon plus carbon plus carbon plus carbon plus carbon plus oxygen plus a bunch of hydrogens, which is going to be up somewhere in this area. So we would expect to see a peak up there at the mass of the whole thing. Sometimes on these graphs you'll get little teeny tiny peaks that are heavier than the molecule you expect. those can be ignored. They are more often artifacts of the data gathering process than actual peaks. The graphs you get on your assessment will be very clear. So once we identify the different fragments of the molecule in this graph, we end up with a molecule which in this case is hexanoic acid. And we know that from, on this graph, the location of the molecular ion peak, which would be somewhere around here, and the presence of ions at several likely peaks. On the assessment, you will not have to identify every peak, or indeed all of them, or indeed many of them rather. You will need to identify 3 or 4 that match up to likely fragments from the molecule that you're working towards. You will not be able to identify the molecule from this graph alone. You will need to use it in conjunction with the IR and 13C NMR that we will be covering over the next couple of weeks.